Hey guys, welcome back. Second video of the quarter. Um, First off, congratulations on quiz 1. I know that the first quiz is always a weird one, right? Um, Nobody really knows what to expect, how it's going to feel, how you're going to do. It's always it's new territory, right? You don't have that knowledge until you've taken that first quiz. So hopefully this first quiz was enlightening in that aspect. I know that people don't like to drop the first quiz, but it's okay if you have to, because again, quiz 1, we're just trying to figure out what it is that it is. I know this one was fairly difficult too. It's a little bit long and you could really feel a time crunch. Another thing I'm hoping people realize is that the note card is not a very good primary source of information. Please do not rely on it too heavily to carry you in this class or help you get an easy A by writing all the information down and just, not studying very much. Note card is useful, to look at really quickly to confirm your thought. Not very useful if you're using it to hold all your thoughts, right? You do want to have a lot of that intuition, all that knowledge, all that chemistry in your brain first and foremost. So that way that when you open your quiz or you flip your quiz over and you start taking it, your brain is firing neurons and saying, hey, do this, do that. And you just look at your note card to be like, I am thinking right, like in the correct way, right? And hopefully the answer to that is yes. So definitely use the note card as an accessory, not as your Bible, right? You want your brain to be the Bible. And it contains the gospel of Dr. Williamson, right? And her intellect and wisdom on the topic. Okay, so again, congratulations on quiz 1. All we can do now is move forward to quiz 2, right? And hope that we are going to do a lot better on that if we are already doing very well in the class. Again, these videos serving as a way to build that chemical intuition so that when you're when you're taking the quiz, you're not scared by anything new that you see. You see the components that dictate reactivity that you've just learned about, and you just put those things together and you come up with your product or with your answer. Okay, so without further ado, let's go ahead and build that intuition in this video on our topic of ethers. Okay. So ethers, usually we talk about ethers with alcohols, right, for that quiz 1, but this one got a little bit pushed back, which is okay. So if you really need to talk about, or if you really need to learn about the attributes, physical properties, stuff like that, you can always go back to that first video and quickly look. I'll just give you the very quick, TLDW version of it, which is just to say that, if I had water and I added an organic component, I'd make an alcohol, right? So if I add this organic chain, I make an alcohol. If I took that alcohol and added another organic chain, I'd have an ether. Okay, and so we talked about this a little bit in terms of, if we look at the polarity, water is very polar, right? Alcohols are just polar, and then ethers are barely polar. Okay, and one of the ways that we kind of figured that out is we said, if I look at water and I look at what it can do, it can make hydrogen bonds. I mean, it's kind of like the standard of polarity, right? And it can make these hydrogen bond networks. We can see that retained in the alcohol because we have the OH. So we have some level of polarity in the alcohols. Usually the smaller order alcohols are very polar. And we can also see this in the fact that alcohols can be very, very soluble in water. So these guys are usually very soluble in water. Okay. If I look at an ether, though, ethers are not very soluble. They're, again, barely soluble in water. And if I think about H bonds, right, there are no H bonds. Right, these guys can H bond with itself. I mean, obviously, water is going to H bond with itself, right? So, those polar interactions are there, but ethers don't have that. They can't do that with themselves. All they really have in terms of polarity is the fact that there's just an oxygen. It's kind of like the only thing that ethers share with with the alcohols in the water is that they just kind of share oxygen. That's why they're in kind of the same family. Okay, so ethers barely polar, barely soluble, right? They have a little bit of a polarity, but that little bit of polarity is something we can take advantage of, because if I have, let's say, 2 components, I have component A and a component B, and I needed these 2 to react, but they don't have sort of compatible solubilities, right? Ether is a great midway in terms of solubilizing these things, right? because ethers are barely polar, let's say A is polar. Well, A will be able to dissolve into ether and be in that phase. And then again, because ethers are pretty much nonpolar, other than being barely polar, let's say B is nonpolar. B is going to have an easy time slipping into, again, the ether there. So we have now an access to a solvent, right? Ethers are very good solvents because they're able to dissolve so many things, right? Both polar and nonpolar. So that's a great thing about ethers. Now, another great thing about ethers, right, on that solvent front, is that if you're a solvent, that means that you're just kind of hanging out, just watching the reaction from afar. You're watching everything mingle, but you're not really like, hitting into anything or reacting with anything. Ethers are really, really inert. Okay, so let's say I take this guy, which by the way, we call this guy diethyl ether or ET2O. That's the name of this guy, diethyl ether. Okay. If I take diethyl ether and I dissolve two things in it, I have really no concern as to whether an ether is going to react, right? Ethers are usually very, very inert, right? Put in something like NABR, which is a very good SN2 solvent, or sorry, SN2 reagent, nothing happens. So this guy is kind of inert to SN2 with a weakly basic anion. Let's say I just amp up the basicity, make it a super strong base like terbutoxide, and I say maybe, I've added the juice I need to get this to react. Turns out this won't react either. So ether is very, very inert. They're just going to watch things flow by, but they're not really going to do anything with them. Okay, which again makes them very ideal candidates for solvents. So then maybe the question is well, wait a minute. Why are we then having a whole video on ethers if they're just not reactable, right? They seem kind of useless, don't they? Well, we can do reactions with ethers. There is a way to crack their hard shell. But before we get to that, right, before we look at what is that we can do to get an ether to react, right, to crack it open, let's actually talk about how to make these guys, because we should know how to make them before we break them. Okay, so let's talk a little bit of prep. Right. Now, the first type of prep we'll talk about, we talked about this a little bit in the last video because I wasn't sure where the cutoff was. So hopefully this is, a little bit familiar, but the first thing we'll talk about is the Williamson ether preparation of ethers. So let's say I have an alcohol and I introduce it to some base like NaOH, right? That'll, NaOH is a base, like I just mentioned. Bases love protons. So this base is just going to go ahead, take that proton. And we make it alkoxide. Now, if alcohols are sort of like these weak, not really interested to react nucleophiles, then their conjugate base alkoxides are super, super strong and juiced up because they have a lot of electrons on them and they really want to share them. So much so that if I have, let's say, like a primary bromide, right, this alkoxide is actually going to do an SN2 type attack on that alkyl bromide and going to attach that organic 2-carbon chain onto the oxygen of the alkoxide, effectively forming an ether. So we just made that diethyl ether right there, right? The one that we just talked about on the other page. Okay, so Williamson ether synthesis is essentially an SN2 type reaction. Sorry, there's like a thing in the way, so I can't. That was a little bit whatever. Anyways. SN2 reactions are useful in making ethers, okay? Now, because this is SN2, remember SN2 is dominated by steric effect. So it's really important that this is a primary bromide, that we don't have anything, preventing the SN2 from happening. If you're really worried, right, you could take this substrate. NaH is another type of base, by the way. It's not a typo. It's not like I forgot the O, this is just another base. But we can make an alkoxide from this. And we can introduce the least bulkiest thing ever, right? The least bulkiest bromide ever, methyl bromide, right? Or CH3 bromide. And this will do the reaction very, very well. Very, very good methylating agent. So we can methylate these alkoxides and make ethers as well. So this would be methyl ethyl ether. There isn't really like a other name for this. Okay. So SN2 reactions, right? All we're really doing is we're taking the OH and we're transforming it to OR. So I guess if you wanted a way to think about it, you could say that we're essentially replacing the oxygen H, so that H there with whatever the alkoxide, or sorry, the whatever the bromide group is in our second step. So in this case, maybe I use this bromide here. So I'll tack here to kind of make this a little bit fast. You do 1, 2, 3, 4. 1, 2, 3, 4. And then on that third carbon, we have a methyl. We have that there. Okay. Now, one thing you'll kind of notice with these two examples is that the ethers, right? Unlike a diethyl ether, these ethers are asymmetric. Okay, so photosynthesis is this very powerful way of making asymmetric ethers. You might remember this from last video, but I did talk about a method of making symmetric ethers, and that method was kind of limited in that aspect, right? In that it could only make symmetric ethers. That was we'll get to it, it's the acid prep. Well, in this case, right, with Williamson ether, we can make symmetric ethers if we wanted to, but we can also make asymmetric ethers, which kind of really brings in their synthetic utility, right? Because we can make a lot more diverse range of these ethers. Okay, cool. Now again, the alcohols can really be anything. Just kind of been using the same one. But like, let's say I have this one, NaH. Actually, let's put it on an arrow. This is how you're likely to see on a quiz, right? Point is to be able to recognize, right, the sequence. So you have like a base like NaH, and the second step of some alkyl bromide. Again, a way to think about it is you're replacing H with the alkyl chain, right? So 3 carbons, so 1, 2, 3. Okay. All you're really doing, and now you've made this nice ether. Okay. Now, one thing you might need to know for like a vocab kind of question, again, primary and methyl, best substrates, right? Because they are going to be very much SN2 favorable. If I use something like a secondary substrate, so let's say on this one I used like this guy here, this is not going to work out very well. So if I, let me actually show the change first. So if I try to make the secondary right up like that, this is not going to work very well because secondary bromides are more susceptible to E2. Okay, so that could be like a vocab thing you might need to know. I'm not sure. Okay, but generally speaking, primary methyl SN2 is going to be very, very great. Okay, let's see. Let's another example we can just quickly write down. I guess something like this. Just trying to expose you guys to like different ways to see it. Right. So again, way to think about it is we see the base and the epoxide, right, are components for this Williamson ether synthesis, and I think, okay, I'm adding this 2-carbon chain, right, to that oxygen there, kind of replacing the H with it. Now this slide you guys can kind of skip. I just want to show this to you guys because this is relevant to some work that I did. I think it's pretty cool. So if you want to, just skip a couple minutes ahead, or if you got the time, kind of hang out, hear what I have to say. So this here is an alcohol that I kind of worked on in my own research, where we would use NaH, very good at deprotonating these alcohols. And then specifically what we introduced to this alcohol, is this bromide here. So we call this propargyl bromide because it's a bromide right next to an alkyne. And what we would get out is this here. Okay. So this sort of like alkyne ether. Now, if I took this alkyne ether and I reacted it with this interesting reagent, right? It kind of looks like a dart almost, right? A nitrogen dart. Call this an acid. But if I react this in the presence of copper, turns out that the alkyne and the acid will actually couple together. They will click together. And what they'll form is this interesting ring here. Let me put the copper up here. Or we'll get this trinitrogen ring, or what we call a triazole ring, okay, where we've essentially coupled together the alkyne and the acid group. Okay, so we kind of combine them together, we click them together, sort of like, clicking in your seatbelt in its lock. This is called a click type reaction. And what makes the click type reaction very important in research, especially my research, is that this reaction is very, very generalizable. You can do it in open condition. You can, do it in the presence of many other functional groups. Usually, a big problem in organic chemistry synthesis is that we have functional group intolerance. So a reaction you want to do, you can't do it because there's other functional groups that might mess with it. This reaction is almost devoid of that problem. It is considered one of the best reactions, one of the most well-known and done reactions in the whole world. It actually won the recent Nobel Prize in bioorthogonal chemistry. So 3 geniuses. Oops, sorry, not CB. That's the initials of one of the people. Sorry, but Nobel Prize, right? 3 people won the Nobel Prize for this. This reaction was so good. So thanks to these people, right? I have, I was able to do some pretty fun chemistry. And they've also kind of changed the lives of many people with this. So thank you to our 3 click reaction innovators. Okay, so just want to show you guys this qualification because this was just something that I did at my time at UC Davis. I just wanted to share that. But click chemistry, pretty cool stuff. And it involves, at least in my work, it involved making an ether. So look at that, right? Doing A-to-B chemistry and Nobel Prize winning chemistry in the same lab. Isn't that kind of cool? Anyways, text your mom about that, right? Cool, right? So on that topic of doing a more complex type of, Williamson ether, there is a type of Williamson ether that's a little interesting. And this type of reaction is going to come up so much in this class. So you might as well learn how to do it now so you don't have to learn about it later. But let's say that I have this interesting substrate here, right? So when I think of like normally a Williamson ether, right, in the way that we talked about a second ago, right? I have a base that takes off a proton, and then I have an O-, and then an O- attacks the bromide, right? Displaces it. And what I get out is an organic piece, right, on that alcohol, or on that oxygen, sorry, that used to be an alcohol. So if I kind of apply this here, where NaOH is going to deprotonate this oxygen, well, again, this oxygen is going to look for a carbon with a bromide, right? If I look on this molecule, I do have this carbon with the bromide. So interestingly enough, this oxygen is actually going to attack itself, sort of like that snake, right? I think it's called, what is it called? Greek mythology, Ouroboros, I think, something like that. The snake that eats its own tail. Well, in this kind of similar scenario, right, O- is eating its own tail, right? Or it's kicking up that bromide on its tail. It's attacking itself. And in the process forms a ring. So the following method I use, it's just a method I use for counting. So I make sure I do make the right kind of ring and do the right thing. You're welcome to use it. You're welcome to not use it. It's totally up to you. I'm just going to show you what I do because I find it reliable, and you're welcome to take it from me if you'd like. But what I like to do is I count oxygen as 1, and the carbon attacks as 2, and I count everything in between. So 3, 4, 5, and then 6. Okay, so that's going to be a 6-membered ring where oxygen's a part of that ring because it's attacked. And if I count like this, right, I know where everything should go, right, based on what number it lands on. So let's say at 4, there's like a dimethyl. I know that goes here, right? Let's say at 2, there was like a methyl. I know that goes here, right? All to help with the counting. But anyways, with this cyclization or with this attack, we have now made a 6-membered cyclic ring, okay? This actually has a name. We call this tetrahydropyran. Okay. So these type of reactions, we call these intramolecular, okay? And this would be intramolecular West. And these reactions are very, very powerful, right? They introduce complexity. They allow us to make these cyclic ether rings, which, originally they seemed like kind of a stretch to do, but totally possible. Now, 6-member rings, very good. You can make those. You can also make like 5-membered rings, right? As long as, again, the carbon count allows for it. So here's another example. Sorry, I'm trying to kind of counting myself to make sure I, draw the right size. Let's say do NaH here, right? I'll annotate on this one, right? O-, I'll tag here. So 1, 2, 3, 4, and then 5. So this will make a 5-membered ring. Right, just like that. Okay, where again, this will be 1, 2, 3, 4, and 5. So if there was anything underneath these, like on 3, there was like an ethyl, I know that would go here, right? So just being able to track where things should go. Okay, but 5-member rings are also pretty good. Usually you'll make a 5 or 6 on the ring size. If you find yourself making something like 7 or 8, something might be wrong. So 5, 6, that's good. But if you're making something like 4, 7, 8, something is not wrong, or sorry, something is not right. It might be wrong. Okay, there is one exception. We'll come back to this, but you can also make 3-membered rings, and these guys have interesting reactivity. So usually it's these 3 that you're going to make. Okay, you're really not going to make these 3 down here. Okay, but yeah, we can have intramolecular Williamson ether syntheses where we make rings. And again, what you have to recognize is that the alcohol is attached to the bromide in whatever context, right? I mean, we see here the most simplest context is just a straight line chain. We see here it's a little more complex, right? There's a ring that kind of holds both groups, and then we kind of cyclize on it, right? I guess we could, if you wanted to, the worst way we could possibly see this is it's like something like this, right? These guys are kind of like a little bit away from each other, but they're still in the same thing. This alcohol, if I deprotonate it, just attack there, right? Kick off the bromide. So we'd get what, like a 1, 2, 3, 4, 5, 6-membered ring. This one's going to be a bit complex. So, let's say if you want to, you can pause and try to draw this on your own. Like go back and see what it was and try to draw on your own. I'm just going to quickly just draw it here. Look at that, interesting kind of ring, right? Looks a little weird, but whatever. Point is that it made a 6-membered ring, so it's probably really good. Okay. But yeah, look out for this, right? If you don't see it on the quiz this week, you're definitely going to see it on a future quiz with some different functionality. So almost every single video until the end of the quarter is going to introduce some kind of intramolecular Wes. That's just how it's going to have to be because it's such a powerful reaction. And I think we'll even see it one more time today too anyways. So yeah, cool. So Williamson ether synthesis, very powerful SN2 reaction. Again, helps us make these very cool, very diverse asymmetric ethers, right? We can also make the symmetrics, but asymmetric is really the utility in this. And what you're probably likely going to see in your quiz, we can also make these really nice ring systems, right? If the alcohol and the bromide are on the same chain, right? Intramolecularity, be very, very familiar with this. Cool. So there is the SN2 way, but we also have the SN1 way, which I like to call the acid way, right? And so this was what we learned before. That was when we kind of took an alcohol and just threw it in some acid, right? So if I'm at like 130 degrees, I have like H2SO4, right? I could take, let's say this ethanol, protonate it because it's an acid, and then another one of these ethanols will just kind of swoop in and do kind of like an SN2 type of attack, right? I mean, primary center, that's all you can really do, right? It's an SN2 type of attack. So what we get out of this, if I just annotate really quickly, right, is a symmetric ether. And so this is really, again, the best use of this type of reaction is just to make a symmetric ether, right? If I take sort of the opposite end of this and I do, let's say, like a tertibutanol, so a tertiary alcohol, right? And I do the same reaction. That second that we make that, tertiary oxonium, right? That water is going to leave because what it does forms very, very stable cation. So now we start to introduce a little more SN1 mechanics. So generally speaking, right, acid mechanism will be more of an SN1 type. Obviously with the primaries, it has to go through SN2. But if I have like a secondary alcohol or a tertiary alcohol as we see here, right, definitely we're going to see the formation of the cation. And then let's say in the case of this one, right, that alcohol adds to make this symmetric ether versus, this alcohol adds to make this symmetric ether. Okay, because again, main utility of this is to make symmetric ethers. Now, there is one way to make an asymmetric ether. We kind of talked about this last time, and it kind of takes advantage of the fact that tertiary alcohols make very good cations. Okay, so in this, I'll annotate again very quickly, but we can make a very nice tertiary cation. But when this cation is alive, right, the best nucleophile in solution is actually going to be the methanol. The methanol is not very bulky, right? It's very, very small. Has a better time attacking cations than this tertiary alcohol would. Like, if you imagine a terbutanol versus the methanol, of these two, this guy is the one that's going to attack. So you do have the ability to make, asymmetric ether. Usually this is the only type that's like linear, right? So if you remember, this is called terbutyl methyl ether, right? Terbutyl methyl ether, pretty cool little ether. I believe it has like applications in oil, like gasoline. I don't remember what though. But we can make that from, from acid. So it is one type of asymmetric ether we could make. But again, not the best, right? I mean, if you wanted to, you could easily make this with the Williamson ether since it's a lot better. Okay, cool. Now, if we take that same intramolecularity that we saw with Williamson ether synthesis and apply it to acid synthesis, I mean, it's kind of the same, right? We just, instead of having an alcohol and bromide, you just have two alcohols. So you can imagine two alcohols like this, and you do H2SO4. And again, between these two, right, if we take that idea that we saw with TBME, where the tertiary alcohol, right here, or the tertiary alcohol ionizes into the cation. So this guy, again, just going to do this very quickly. I apologize for my speed. If it's a little too quick for you guys, let me know. And I'll slow down a little bit in the next one, but I just want to make sure we get through these like with enough, within a good amount of time. But when this ionizes, so it forms a oxonium and it leaves, right? Form a carbocation. Again, we have this alkyl here with an electron pair. Go ahead and attack. So let's go ahead and do our counting. 1 attacks 2, 3, 4, 5, and 6. So 6 on the ring. And again, if I do my counting, 1, 2, 3, 4, 5, and 6. Right, look at that, carbon 2. Right, we tacked on carbon 2 and it has a dimethyl, so we add that in. And so now we have a THP derivative here, right? Just a dimethyl THP. And there you have it, right? We have an intramolecular acid ether synthesis. Again, you can really diversify this in a lot of different ways. For example, I could have something like this. Just, I mean, I'm just like spitballing at this point. It's just randomness. But let's see, right? This guy probably ionizes, right? Because it forms that cation like we saw in that example for TBME. And then this alcohol can cyclize onto it. So 1, 2, 3, 4, and 5. Okay. Again, just training your eye to seeing these. Again, it's not really no one should really be trying to find every single possible version of this kind of question, but it's just to train your eye. We see two alcohols and we see acid, maybe at 130 degrees, right? No one should really be surprised that these guys are going to kind of cyclize on themselves. Okay, cool. So intramolecularity, again, it's going to just show up a lot. It's a very, very good reaction, very, very powerful. In modern synthesis, the more intramolecularity you have, the easier your reactions become. Because again, if you already have the functionalities available in the molecule, then of course they're going to react with each other, right? They're just there. You just need to motivate them, maybe massage them into doing what you want with a particular like acid, right? Or maybe like a base or something. Okay, cool. So in terms of making ethers, right, we have our SN2 Williamson ethers, right? We have our acid SN1s, right? Don't really have a name for this, so we'll just call this acid alcohol, I suppose. But that's how we can make our ethers, right? That's how we can make them. And now that we know how to make them, right, we should learn how to break them. Again, if I look at an ether, right, these guys, I mean, they're so inert. The base, right? They really don't want to do anything. They kind of just want to hang out. I mean, if you kind of look at, if you can look at diethyl ether, it kind of looks like a guy. It's like really happy. It's like, on the side, like, woohoo, like I'm happy that things are reacting around me, but I'm not reacting at all. Okay. So, what do we got to do to get this guy to react? How do we get this guy to like start, doling out punches or taking punches? Well, it turns out the way we do it is going to be with very strong acid, which might be kind of a surprise because we used, in one of our syntheses or in one of our preparations, we used acid to make them. So we're using the same thing we used to make them to destroy them, right? Kind of like something, your mom would say, right? Like, I brought you into this world so I can take you out. Kind of the same idea. Okay, so let's kind of look at how this works. So let's take, diethyl ether, right? Primary ether, simplest ether, and just throw it in some acid. Okay. Again, if we're an acid, we have a lot of proton in solution, right? And if you have a lot of proton, might as well just protonate something. Actually, instead of H2SO4, let's just use HX for now. This is a good choice. Okay. So if I have an ether, go ahead and protonate. Right. Now we talked about this before, right? Ether is usually not very polar. The only polar thing about them is they have an oxygen, right? If I take that oxygen and I put a positive on it, right? Think about what that does, right? Oxygens are electronegative. They really don't like positives. This positive is sort of like a migraine. And when it gains that positive, any polar effect that we have, it's going to be multiplied intensively, because unfortunately, the only way to solve oxygen migraines is with electron excitation, right? So oxygen totally increasing its pull on those carbons, incredibly increasing those dipolar moments and inducing a lot more reactivity. Because before, where X minus might have just looked at this ether and walked by, now this X minus looks at this ether and it thinks, oh, this guy really thirsting for an attack, right? This guy is way more welcome for an attack than previously before it was protonated. So in the case where we have, two of the same primaries, it doesn't really matter who we attack, but when we do an attack, it's going to be an SN2-like attack on this primary center. So sort of similar to alcohols, right? Where primary oxoniums, were subject to SN2 type of attacks. So when we break this ether open, get an alcohol, and we get analyte. Yep. So primary ethers susceptible to SN2 type of attack, which again, right, SN2, a very good reaction to do if there's not much hindrance. So let's say that I had a primary ether, right, that wasn't so symmetric, like diethyl ether, right? Maybe I have an ether that looks like this, right? If I do that same HX type of attack or HX type of condition, right? I have the protonation. Actually, just for the sake of time, because I've already kind of drawn it here, I apologize. I'm just going to annotate a little bit. Let's do it on here first, right? But I will still write HX here, so we know that that's the condition, right? When X minus comes here to attack, again, we're thinking about least hindrance, right? Less amount of sterics. Which carbon, right, flanking this oxygen is going to provide, right, is going to satisfy that criteria. Well, if I look here, I see primary, that's next. In this case, this one's next to a methyl. This one's next to a secondary carbon. Which carbon would be more steric and therefore less available? Well, this is secondary, right? That's a lot of bulk. So, if I was X minus, I wouldn't really want to fly into that, right? I wouldn't want to get smacked in the face by that secondary bulky center. So when we have two primary carbons competing, right, X minus is going to go on that less hindered primary. Because again, this is an SN2 reaction. You want the least amount of hindrance. Okay, that says hindrance, by the way. I know my handwriting's bad, I apologize. Okay, and so what we're going to get is X cleaving that left side, the alcohol on the right side. Okay, so X cleaves the left side, alcohol on the right side. So then the question becomes, okay, well, obviously hindrance is a big thing in SN2. What if I again use that very not hindered group, right? The least hindered group possible, a methyl group. Guys, I want you to write this down in your brains, right? Not your note cards, in your brains. Anytime you see a methyl group and you see like a primary or even a secondary right? That methyl group is the group that's going to get cleaved in acid. Okay, especially if you're doing like an HX type attack, SN2, right? That methyl group can get cleaved almost instantly, right? No doubt in our minds, the halide is going to go onto that CH3 group. Okay, so with that being said, you can start to build a little bit of hierarchy here. Primary, right? Very fast reaction, but methyl is going to be a bit faster. And both of these are kind of dominated by SN2, right? Those are the mechanics that explain it, right? That's why methyl is faster. It's because it's by an SN2 attack. Okay. Now, one thing I'll kind of explain now, and maybe we'll come back to it a little bit later too, is that in these reactions, I've kind of only reacted HX once. So one thing I kind of assumed is that HX is that one equivalent. What that means is that for every ether, there's only one HX. So HX can only react once. Okay. The significance is that if I don't have one EQ, or on the other hand, I have something called excess HX. So now they're saying this is excess, right? So like a lot of it, so more than one equivalent, so that there's more than one HX per ether. Well, that HX can react again. And particularly, right, it's not going to react with the halide, but it is going to react with the alcohol. So if I have excess, right, these questions are always the best because excess means that both things, right, both sides of the ether cleave to form an X group. Okay, so I don't have to really think about which side would react first. It's more of, let me just destroy the ether completely and, add two X's to it. Again, we'll come back to this again. I just want to introduce this idea right now that every single reaction we're going to look at for the time being is just going to be at one equivalent. So we're looking at if I had one HX, how would it break the ether? Because that's the thought question, right? There really is no thought behind excess. It's just you're able to cut an ether in half and, throw X's on each side. Okay. But we're going to first talk about AHX and one equivalent, and then we'll start to have a little more fun with the excess. Okay, cool. So primary carbons, right? SN2 dominated, methyl, gonna beat them by a long shot, all SN2. So what happens then if I take a primary and I do a reaction, or let's say I have a primary site and a secondary site, right? What's gonna happen? Well, again, HX, gonna get protonation. And when X minus approaches for its attack, turns out the primary side cleaves open. Okay, which is kind of interesting because in alcohol chemistry, right? Back in alcohols, we kind of said that alcohols would form cations on secondary centers as well. Turns out that's just not the case with ethers. Okay, so with ethers, primary and secondary are both going to be influenced by SN2 mechanics. Okay, and because SN2 is all about less hindrance, right? X is going to cleave on that primary side. Okay, so if we want to update our hierarchy, looks like secondary is losing right now. And it loses to everyone. Again, do not for a second hesitate. If you ever see something like this, where you see a primary end, I don't want any of you guys to hesitate. You're cleaving that primary end and you're putting X right onto that. Sorry, if you see a methyl end, my apologies. If you see a methyl end, I don't want any of you hesitating. You're immediately putting X on that methyl end. No questions asked, right? Pretty simple. So secondary kind of loses out in this battle here. Okay, so again, all these SN2 reactions looking for least amount of hindrance. Okay, and let's say that we were doing a reaction with a secondary versus secondary, right? Where both of these are secondary, and we couldn't really tell, which one's different. They're both secondary. Well, if it's one equivalent, there's only one equivalent of the HX, right? We don't really know where it's going to go. This is kind of like the only scenario where a secondary kind of wins, but it doesn't really win because we don't know if it cleaves on the left side. So if it does that, it makes an X here and then mixes here, or it cleaves on the right side and makes this X here. It's like, oh, I don't really know where it's going to go. So this is kind of like the worst possible one. Hopefully not going to see something like that, but if we do, right, we're going to be a little bit prepared. Now, if I were to see something like this, I would expect it to be in excess, right? Because again, remember, if we're in excess HX, the most beautiful example, because in excess, everything just turns into X. So both sides will just turn into X. So I could see a question like this being asked in excess, not really have one equivalent though. Okay, so again, secondary kind of loses out to everyone. So what's the deal with tertiary, right? What's going to happen there? Well, if I have a primary and a tertiary, right? Again, if everything is dominated by SN2, then you would think, okay, tertiary is going to be the loser here. Primary wins, has to. But it turns out that the second you protonate this tertiary group actually ionizes and forms an oh so sweet and stable tertiary cation. And again, if I have an X minus, something with the lone pair, X minus is going to capture that cation very, very easily. And what we get out is that tertiary halide. Okay. So, whoa, that's kind of crazy. What this means then is that because that tertiary group ionizes the fastest, not only does it beat primary, right? So tertiary now beats primary, but it also beats secondary. Okay. Imagine that, right? SN2 reactions getting beat by an SN1 type reaction. But it should make sense, right? Because tertiary is the best at SN1. So you're kind of asking someone who's kind of an apprentice or like, a senior, and you're like, oh, you know what? Like, I want you to fight the master, right? They put up a good fight, but they're not going to be as good as the master, right? So if I have like a kind of secondary here, again, not even hesitating, tertiary part falls off. And what we get is the tertiary halide, secondary alcohol. So then what would happen if I had TBME? Right, so I have the terbutyl methyl ether, where I have the tertiary center that is the master at SN1, and I have the methyl center, which is the master of SN2. So now you've got two masters of different schools fighting each other, right? Who do you guys think is going to win? Right? Let's all pretend that I'm like a bookie and I'm taking your bets, right? Put in your bet. I'll give you like 5 seconds. Put in a bet. Who do you think is going to win? Who do you think is going to be the better choice here? Okay. Turns out that it depends. What? Oh my God. Jim, you told us that you knew the answer to everything. I do know the answer to everything. That's why I know that the answer to this is that it depends, right? It turns out that when you have two things that are really, really good at their own reactions, everything's going to matter, right? The condition's going to matter. The temperature is going to matter. The concentration is going to matter. How much you prayed that day is going to matter. It even boils down to luck, right? How lucky are you that the side that you want to win wins? So in this class, because again, we're not all masters of the content, we're just learning. It doesn't really make sense to ever ask you guys what's going to happen if I do one equivalence of cleaving this kind of ether. It really doesn't make any sense. I mean, it's a really difficult question to answer, right? Because these are essentially, the same. So we are going to say that these two are the same, okay? But if we ever have these two masters fighting everyone else, right, which is definitely going to be the case, right, on your quiz, right, we know that they're always going to win, right, their respective battles. So methyl will always be primary, secondary. Tertiary will always be primary, secondary. But in this fight between each other, it's going to be very equal. Not a very good thing to ask. Okay, so very good thought experiment, and hopefully, maybe one day if you guys ever do this, the side that you want to win wins. But again, it's really context dependent, and unfortunately, we're not that level yet where we really need to know the answer. It's just better to know that this is a very hard comparison to make, very, very hard. So we never have to worry about it on the exam. Okay, but again, and every other battle, right? Just know who we're supposed to win, right? And just use this hierarchy. Okay, cool. So HX cleavage of ethers, pretty straightforward, right? You protonate on the ether, right? So kind of draw the mechanism here, protonate on the ether, and then you use the nucleophile in the solution, right? Usually X minus to attack if it's primary, right? Or if it's tertiary, just go ahead and ionize, right? So if you do an SN2 attack, do an SN2 attack, or if you do an SN1 attack, do an SN1 attack, okay? And once again, everything we've kind of talked about here has been at the one equivalence level. So if there's a 1 HX for every ether, so that we get an alcohol and an ether, sorry, an alcohol and a halide. If you ever have excess, you know, that's like a time to say hallelujah. Doesn't matter who you believe in, just say hallelujah. Because excess just means we're going to turn both sides into halides. And our thinking doesn't, we don't have to really think too much about that, right? We just kind of draw it. Okay. But also means that probably not going to see that question very often. Okay. Because again, that's not the type of question that tests your ability or tests your knowledge on the system. Now, just like there are linear ethers, there's also cyclic ethers, right? Remember THP, right? We talked about THP, right? Or, you know, THF, right? These guys have derivatives, and these derivatives can also react. Don't be afraid of cyclic ethers, like I mentioned, or I might not have mentioned, but I'll mention it now. THF, this guy here, is basically just the cyclic version of methyl ether, right? Just if there's a bond here. So really the reactivity is no real different. I mean, THP is just if it's like propyl groups, right? Anyways, don't be afraid of these guys, right? Don't be afraid of them. They're exactly the same in terms of how we make our judgments, right? We look here, and we apply the hierarchy, right? Who should win? So if I look at THP derivative here, right, I have a tertiary side and a primary side. Based on my hierarchy, tertiary wins. So what I'm going to do is I'm going to just draw the cycle with that side broken. So I'm going to break this bond here. I'll add, let's say it's like an HBr. Right, I'll go ahead and put a BR there. I'll make this an OH. And guess what? This is a correct answer. Yeah, you don't have to change this anyway. I know some of you might be motivated to make this linear, but who cares? This is correct. Just write this and move on, right? That's a correct answer. That is exactly how it's going to cleave open. Same thing with this guy, right? Let's say I do this in like HCl, right? I see here a secondary, I see here a primary. Primary is going to cleave based on my hierarchy. So I'm going to go ahead and draw this, make this an OH, and then I'll put a chlorine here. Again, this is a correct answer. Don't overthink it. Don't stress yourself out. Draw a correct answer and just move on, right? That's all you got to do. So many times I see people try to unravel these and they make a slight mistake and it costs them, but it's like, why? You know, just do the easy thing. Just break aside and add your halide, right? Move on. Yeah, have a great day. Again, if this is an excess, oh my God, that's great. Because who cares what side it breaks on? Right? Break any side. Just, you know, put two halides. Right. Let's say this is an excess as well. Break two sides, just put two halides. Yeah, not very likely, but it doesn't hurt to see it because it's like a very nice and clean and easy reaction. Okay. Cool. So there you go. That's the secret to breaking ethers, right? Cracking open these hard shell eggs, these ethers here, so we can make a nice ether omelet. All we've got to do is use a strong acid, right? And so the usual culprit that you'll see for these is going to be halide acids, right? Because one, they're really strong acids, and two, they allow for testing on, you know, where does the halide go at one equivalence. But you could also see other conditions, and these other conditions can be a little forgiving. For example, let's say that I had this, but I did the reaction at H2SO4 and water, or dilute H2SO4. Okay, how does this work? Well, again, get a protonation. And so we'll look here and here. We have a primary and a tertiary. In this case, tertiary wins, right, based on our hierarchy. And mechanistically, right, that means that we're going to have an SN1 ionization. Right, so we'll form like a cation here. Okay, and so if I look at what's in solution as a nucleophile, I have HSO4 minus, I have water. And if you're not sure who's the better nucleophile, that's okay, because I'll just tell you. Water is what's going to add here. But what makes this so interesting, and also another kind of freebie question, that when I add the water, I kind of look at the adduct. I just like stare at it a little bit. Wait a minute. this is just like excess HX, right? Because in the same way how excess HX will break open this ether and give me two X's, well, hey, if I add an H2SO4 and water, this will also break open both sides, but it just adds two OHs. So look at that. We now have two possible conditions where thinking is thrown out of the window. And that's the best thing. We don't want to have to think. We just want to have an easy way to answer these questions, right? H2SO4 that's dilute or XSHX are going to be those questions. Okay, so let's really, really hope that we see those because that'll make our life really easy. But I mean, there's a likelihood that that might not be the case, which we have to accept that. Okay, so be very, very comfortable with this hierarchy and applying it to the 1EQ right, condition of HX additions. I think once you do a couple of these, especially with the practice problems that Dr. Williamson gives, you guys will be experts on that. Should be experts on breaking these ethers. These are going to be something that's not going to be hard to do at all. And again, it just takes practice. It just takes, familiarizing yourself with the system. If at the very least, right, you're not able to, immediately visualize the answer is, and be able to walk yourself through the mechanism, right, and understand the hierarchy, and you most likely get the correct answer. Okay, cool. So again, when it comes to normal ethers, right, we now know how to make them, which is through that Williamson ether synthesis, right? We can do that in SN2 fashion. We can also do sort of the acid synthesis, which can make symmetrics, but you can also do asymmetrics, right? That one sort of example. Keep in mind the intramolecularity aspect, right? That we can, as long as they're tethered together or on the same molecule, we can make these nice, beautiful rings. And that also applies to the acid synthesis as well, okay? That we can make these nice ether rings. Okay? On that note, right? If we make, if we can make ethers in acid, we can also break them in acid. So, make something just to break, take it away, which is kind of funny to me. And so this is where our hierarchy comes majorly into play, right? In knowing that methyl and tertiary kind of the kingpins of the ether openings, but they kind of dominate on the primary and secondary. You're always going to get a comparison between one of these two and these two, right? Or, maybe one of these two and these two. Again, really the only time you should be making a secondary halide, as we saw back here, was if we have two secondary sides, right? In that case, if we have one EQ, we'll make 4 different answers because we don't know what side it will cleave. But the better question is excess, right? Because then we'll have 2 answers, easier to write down, easier to think about, not much to stress about. Okay, cool. Well, that is normal ethers. And I bet a lot of you are thinking, Jim, what do you mean normal ethers? Well, remember, back here when we talked about Williamson ether synthesis, I mentioned that 5 and 6, right? Those are pretty normal ethers to make in terms of ring ethers. 4, 7, 8, not so much. But 3 was a little special, right? 3 was a little bit interesting. So let's go over here for a second and let's talk about those 3-membered. So first off, how we would make them, pretty simple. If I want to go the West route or the Williamson ether synthesis route, right? I take an alcohol and right next door, I install a bromide. Okay, so I have this guy here. If I have some kind of base like NaOH, which again, just to annotate that, we'll just remove this proton and make it O-. Again, O- is going to be motivated to kick off that bromide that's next door. And what we get out is this 3-membered ring here. Okay, we have a name for this. We call this an epoxide. Okay, now epoxides are really interesting characters, right? They're these triangle ethers, which when you look at the shape, you might think, wow, isn't that shape like incredibly strained? I mean, 4 wasn't acceptable, right? That looks like that. 5 and 6 were because we learned back in 8A that they were good. So what is about the 3, right? Why is the 3 so good? Or, why is it even allowed to form in the first place? We will get to those questions, right, and answer those questions. But first, let's just talk about the preparation, right? If we get the preparation out of the way, then we can understand the reactivity and not have to worry about, any sort of like sneakiness on prep, how to make these that could come up on the quiz. Okay, so again, the West method, fairly simple. We have an alcohol right next door to a bromide. We actually have a name for this. We call this a vinyl bromo alcohol. Okay, so what does that mean? It means that we have 2 carbons where one has an alcohol, one has a bromide, right? That's a vicinal bromo alcohol. But we treat that with base and we get an epoxide. Here are a couple little rules that you might want to be aware of when it comes to this. Okay, first off, let's say that the alcohol is a wedge, right? So just like that. And we do this reaction. So I'll use NaH this time. Well, because the alcohol is a wedge, when this attacks, actually the epoxide will also be a wedge. Okay, so if my alcohol in my bromo alcohol has stereochemistry, then I know exactly what the stereochemistry on my ring is going to be. In this case, it's going to be a wedge ring. Okay, could have also been dashed. It's totally fine. Let's actually use a different example just to expose you guys to all the different types. So let's say the OH is a dash. Here's actually a little requirement. I don't know if you need to know this. Only worry about this if Dr. Lewis mentioned this, but the OH and the BR in this method have to be opposite of each other. They have to be anti or trans to each other. But if you don't need to know that, don't worry. I'm just mentioning it just in case. But when I do the NaH and I remove this proton here, right, again, doesn't matter what the bromide is. What matters is that the oxygen is a dash. So, or sorry, the alcohol is a dash. So my epoxide will also be a dash. Okay, so this method allows for pretty strong control, pretty strong control over what that epoxide will look like. And that might come in a little handy when it comes to the openings. Keep that in mind. Okay. Now again, if I do this NaOH, remove that there, get rid of that bromide. And again, since that alcohol was a dash, so will our epoxide be a dash. Okay, this methyl here is just hanging out. It's going to be the same. Okay. Now, it's not required that there's stereochemistry. Like, I mean, it's totally possible that you might just even get like, oh, I don't know, like just this. That's totally fine, right? Don't just make stereochemistry because you have to. Only do it if it's given to you, right? Only do it if it's given to you. In this case, again, we know that this is going to depronate here. It's going to break there, or attack there and break that bromide bond, right? Form that 3-membered ring. Okay, so if we go this route, right, the bromo alcohol route for epoxides, if the alcohol has stereochemistry, that is going to determine the stereochemistry of our epoxide ring. Again, that is going to be a little bit important, so it's good to know this for now. Okay. Now, there's another way that we can make epoxides. It actually starts from an alkene. So back in 8A, right, we learned about alkenes. Maybe not this particular reaction, but if I react MCPBA, don't worry how it works. Just know that it does. Right? MCPBA form an epoxide on the 2 carbons that were the alkene carbons. So alkene there, epoxide there. Now, unlike the bromo alcohol, there is nothing to indicate what the stereochemistry should be, right? So in this case, like I have no wedge or dash to tell me whether this is wedge or dash. Because of that, that means that MCPBA will actually form both isomers. This is really important because I could totally see a question on your exam, sort of like this one, where you're asked to make an epoxide with MCPBA, and you will have to draw both isomers, okay, to get full credit. Which that's kind of crazy, don't you think? Like, there is usually not an indication on your exam that you need 2 isomers, right? But you'll just be expected to know. MCPBA is one of those examples. You are just expected to know. You just need to know that MCPBA will make 2 isomers. And when I react this, when we learn about reactions in a little bit, right, you will also be expected to know that there will be 2 answers, right? Because there's 2 epoxides that form, so there's 2 different epoxides that can react. Okay, so I could totally see this being on your exam, knowing this. Okay, so you're welcome if I guess that. Okay, we'll just do one more. Again, MCPBA will just make an epoxide, and because I do not know anything about stereochemistry, I have to assume both epoxides form. Okay, so two main methods for making epoxides. I can either do it from an alkene, right? And actually, you know what? Just for now, I'll just not have to worry about stereochemistry. Or, so I can do MCPBA. Or I can do it with base as long as I have the bromo alcohol. Also, it doesn't really matter where the bromide is or the alcohol is relative to each other. Like it can look like that. It can look like that. Doesn't matter. As long as there's some base to deprotonate the alcohol can slam shut on the bromide, you're going to be fine. Okay. Again, it's all about recognizing that we need to do this. Okay, cool. So that's how we make epoxides. But again, what are epoxides? What about them? You know, why can we form them? Why do we even see them in the first place? Well, when we do ether formations, right, especially when we do the preparations of those cyclic ethers, right, again, the reason why 5 and 6 are so good is because 5-membered rings and 6-membered rings have very little strain. There's barely zero strain. There's a little bit in here, right, but there's zero strain in the 6-membered ring. So that's what makes these guys really good. But when I think about, you know, the chance of making these rings, so this might be a little bit difficult to think about, so I apologize if I do a bad job explaining this. But like if I kind of draw like the linear chains that kind of make these guys, right? Think about the amount of chance or the amount of luck that you need that the O minuses kind of, you know, slither into some position where they're able to attack this bromide. Like I know we draw this arrow, but really what we're saying is that oxygen, you know, kind of lines up in a way that it can attack that carbon, right? I mean, the conformation required, that's like 1 in a trillion, right? Even more so, I mean, 1 in a quadrillion, maybe, when we add extra carbon, right? That amount of rotation, the amount of conformations you add, it's a bit unpredictable. Another way to summarize this is that there's a lot of entropy, right, associated with these ring closures, right? You have to really be hopeful that your bromide and your alkoxide are in that correct conformation. And the more carbons you have, the more conformations you have, the less likely this is possible. So while these guys are really stable, at least in terms of entropy, at least in terms of, you know, how lucky they are in being in the right conformation, that part is very low because the oxygen and the bromide is still a bit far away. So it's like, oof, I'm not sure, you know, obviously it's going to happen, but, you know, oof, that might take a little while, right? It might take like 30 minutes, right, for it to find the correct place to attack because it has to accidentally slip into it, right, into that conformation. On the other hand, right, so this is sort of like the stable case, but on the other hand, the triangle, right, the smallest shape possible, incredibly unstable. This thing wants to react like crazy, right? I mean, we'll see that actually epoxides can react with a lot of things that even normal ethers normally don't react with. So why is it then that if they're so unstable, these guys are forming? Well, think about it. The oxygen and the bromide are incredibly close to each other. So this game, right, the Vumafu. Oh, that's so crazy. Why did I say that? I said Subumafu. I don't know. It's kind of late. I don't know if you guys remember that. That was the dude with the lemur. I don't know what lemurs look like. Whatever. Anyways, funny word. But when we think about the ability for this O minus to slip into the correct conformation, I mean, they're right next to each other, right? They're as close as possible. So it is very likely that this O minus is, you know, already primed for attack, you know, by the time it's deprotonated. This ring forms super fast. So like if these rings take like 30 minutes to like 1 hour to form, this takes like 2 minutes, right? 5 minutes, right? Super fast. So it's not really about a stability thing. it's more of like it's primed for that cyclization, and it's there. We call this a proximity effect, right? So if I want to put a term here, I guess we put proximity, very high proximity effect in the epoxide formation, very low in the 5-membered and 6-membered. Okay, so it's kind of interesting how that balances out, right? You can either be very stable and the system, usually tends towards that stability, or you can just have everything in the right position, just maybe not as stable, but it's there, right? And they're ready to react, so they just do it anyways. That's the magic of the epoxide and what it forms. But again, because it's all very close and tight and packed in, very, very unstable. And so that means that the reactions are going to be very, very interesting. Okay, so let's just start with a standard epoxide, the one we started with before. And let's just do an HBr reaction, right? We did with the other, like we did with the other ethers, right? Just an acid opening. We know this will work. So again, take epoxide and we protonate it. Okay. So one really cool thing about epoxides, and sort of the inspiration for the title of this video, is that because epoxides are triangles, and really this applies to all triangles in organic chemistry, but triangles are really strained. I mean, if you think about a normal bond, like a normal carbon-carbon bond, usually those orbitals are lined up very, very nicely, right? They're usually very linear, very straight. They overlap over each other, make a nice, very nice strong bond. But because of the triangle and sort of the strain associated and the angles associated, you can't really have very straight orbitals interacting. If anything, the orbitals start to kind of turn and curve. They start to bend a little bit. I mean, look at that. I mean, what did I just make? I think I just made a Chiquita banana, right? It turns out that the bonds in epoxide and any triangle really, right? The bonds are not linear straight bonds. They are curved banana bonds. Wow. So really, these bonds are really, really strained, and they're really looking to react as much as possible. And if you want to know a way to think about it, right, epoxides don't really have real bonds. They have kind of like fake bonds, sort of like this. Again, not very real. Try that a little bit better. Okay. And so when you protonate an epoxide and you kind of, again, you give this oxygen that migraine, right? How do we solve the oxygen migraine again? We give it electrons. So on both sides of these both sides of this epoxide, the dipole starts to increase. Now, this is where epoxides kind of differ from other ethers, right? This is why I mentioned earlier that we were talking about normal ether reactivity. Epoxide reactivity is special. In acidic solution, when you protonate on the epoxide and you start to cause these dipoles, it turns out on both these carbons, you get positive character, but the side that is more willing to stabilize that positive charge increases in that positive character. So let's say that there's a positive charge here and a positive charge here. So we'll call this left and right. Because the left side is more substituted than the right side, it turns out the left side that's more capable of stabilizing the positive actually increases its dipole relative to the other side. It starts to take more of the weight, right? Because again, these aren't really real bonds, right? That oxygen's like looking to depart. And really, if it's going to depart, it's going to leave a positive charge somewhere. Better to leave it on the side that stabilizes better than on the side that can't. So in acidic solution, right, epoxides are going to open up on the more sub side. So when Br minus makes a move, it makes a move on this side here. So if I kind of draw the direct result of this opening, right? So make sure to draw the epoxide, right? If I kind of draw the direct result, I get rid of that bond on the side that we broke, and I replace it with a bromide. Okay. Now, for the time being, I just want you guys to focus on the reactions right now, just to kind of be able to predict where things go, and then we'll look at stereochemistry. So for those of you that are like, oh my God, there's stereochemistry, why are you not drawing a name, blah, blah, blah? It's okay, right? We're gonna look at how these systems react, and then we'll talk stereochemistry at the end, because that's a bit more of an advanced topic, right? Cool. So in acid, if you can identify an acidic condition, right, you should open up your epoxide on the more sub side, or essentially on the side that stabilizes the cation better. Okay, so what are some other acidic conditions? Well, I mean, really the most popular one that we tend to see is HX. So HX is very popular. If you see it, you know it, right? So in this case, right, we'll protonate on the epoxide. And if I look at this carbon here, right, which side is more substituted, more willing to, you know, stabilize the cation? It's going to be that top carbon. So we're going to go ahead. I mean, again, if I kind of just draw the epoxide here, we can erase the bond with that there. It's a little messy, but we'll just draw it in for a second, right? We'll put X here, right? If I want to kind of clean this up, I can just put OH a little bit more down, give more space for that X and do that. And again, at least for the regiochemistry, at least for where X should land up, we are correctly predicting that. Okay, exactly where X is going to show up. Okay. One of the easiest ways to kind of recognize that something is an acidic opening, again, is to just look for acid, right, in that reacting step. So, for example, sometimes you'll see like H2SO4 and H2O, right? In this case, when we react, right, again, if I look at the left carbon and the right carbon, right, which carbon is more substituted and willing to react in acid, it's going to be that left carbon, right? So when I open this up, again, if I just kind of draw the epoxide here, I can kind of erase this bond, right, make this an OH, and again, I'm adding water, so let's add an OH here. So hey, look at this. This reaction is kind of interesting. It just kind of adds OH on both sides. That's kind of cool. That'll work out. Okay. Cool. Cool. So again, just an acid, look out for that. Find the more subcarbon, break the bond on that side, and add the nucleophile where it's supposed to go, right? One little tip I will give you guys, because I noticed this mistake a little bit, which is okay, no big deal. It's just something that I noticed. Sometimes you guys will like accidentally put the OH and whatever the nucleophile is on the same carbon. One little trick you can use is that always, whenever you do an epoxide opening, both your functionality should be like, you know, there should be like two carbons away from each other, or it should be like a 1-2 kind of thing going on like this. That's a great way to check you're doing it correctly. Another thing to make sure you're doing, because I see some people mess this up too. A lot of people, when they draw this, they think that this whole oxygen is leaving, so they kind of get rid of it. Always, always, always in epoxide openings, we're going to see this. The epoxide O always turns into an alcohol. Always. Anytime you see an epoxide O, it turns into an alcohol. So we should always, always, always see at least one alcohol in these reactions, right? Let me show that it's attacking here. It's attacking here. Okay, do it there. Okay, cool. Again, we'll go over these tips and tricks again. I'm just trying to, again, expose you guys to them initially now. Cool. So in acid, right? Actually, let's do another one. If I can think of another one. Okay, there we go. Not very creative, I guess. Let's do a different one. Yeah, let's do this one. Right, and let's do H2SO4, but in methanol. That's a good one. Okay, again, we're gonna get a protonation. And then when I look here and here, what side is my methanol probably going to attack? What do you guys think? I think that I wish that there were people in the audience so that someone can answer that. It gets a little boring and lonely sometimes doing these by myself, but it's okay. Methanol is going to go ahead and attack on the more side, which is the left side, sorry, on the left side. So if I kind of just redraw this again, epoxide, but I erase this bond here, right? It will be, okay, it's kind of hard to draw, so we'll kind of have to do a little bit of rearrangement. But I'll put an OH here, and then we'll put like an OCH3 here. Okay, this looks really nasty, so I can kind of redraw it, right? Okay, cool. Again, for stereochemistry at the time being, let's not worry about it. Okay, let's just get the correct opening first, and then we'll worry about the stereochemistry. Okay. Oh, and again, right, remember this oxygen here turns into this alcohol here. And I can also just make sure that these guys have like sort of that staple relationship, you know, that they're like 2 carbons away from each other. At least so far, these have all been obeying that. It's great. So just like normal ethers, epoxides react to acids. It's just that it's always going to be the more sub. So there's no like confusing relationship. Always open up on the more sub. Now, where things are a little bit interesting is that actually these epoxides, because they're so reactive, these guys will also react to base, which is kind of interesting. Because again, ethers, I mean, if I have like THP, for example, and I try to do a reaction at base, we saw this before, like if I do a reaction at like RO minus, right? Absolutely no reaction, right? There's not enough juice to break this open. But if I do the same reaction, but on the strain epoxide system, turns out it's going to open up. So let's say that I have this here. Right? Again, basic condition because I don't see any acid like HX or H2SO4, but I do see a basic O-, right? If there is no proton in solution, right, we can't really take advantage of the cation explanation that we did before, right? So back here, we said that because of the cation and that migraine, right, the higher degree of carbocation characters would dictate reactivity. But over here, there is no cation. So sure, it might be a migraine, but it's not. I mean, it's more like a dull headache. So when it comes to these systems, it turns out the selectivity is flipped. Where acid prefers to attack on the more sub side, base prefers to attack on the less sub side. And so in these cases, right, we will have attack, on this case, we'll have attack on the right side. So we can go ahead and remove this bond here. And what I'll get is an OCH3 here. Okay, so once again, this oxygen becomes this guy here. And we're retaining that staple kind of relationship, right? Making sure that those guys are, you know, related in that way. Okay. You can also, you know, for those of you that are drawing these along with me, you can also draw it this way. That's okay. Again, focusing on just making the right relationships right now, the correct openings, and then we'll focus on stereochemistry and how that should work. Okay, let's say that I have this here. You know, really when it comes to basic solution, it's about, you know, just familiarizing yourself with the reagents, because the reagents are a little bit weird. There's a lot of them, and a lot of them are new. One of them in particular that might be new is this alkyne reagent, right? If I react it with an alkyne, again, minus charge, right? Carbon anion, right? That's going to attack on that less sub side. Kind of a new reagent, might not be used to seeing that, which is okay. It's totally okay. So we break this bond here, but we're going to form a new one with the alkyne. We'll put an OH here, right? Again, making sure that this oxygen becomes an alcohol, and then we have that sort of staple relationship with that nucleophile. Sounds kind of interesting, right? Because we're just kind of, it's like we're extending it with carbon. That's not something we've really seen before. Actually, in 8A, we never really saw that. 8B is kind of the first time we've seen this carbon-carbon bond forming. Look at that new reaction. Interesting, right? Okay, cool. Let's do this one here, right? Another sort of carbon minus reagent that you can see is if you see like an Li, or you can see an MgBr. Okay, so a new reagent has entered. Kind of sucks that you guys are learning this on the go and not like, you know, after you've actually learned it. This is something new, but you won't really talk about this for a while. So it kind of sucks, but it's okay. We're all smart kids. We can add this and figure this out. I would highly recommend, if there's any reagents you're not familiar or comfortable with, like this is where it's a really good time to like put on your note card. Like I would probably put these on my note card just to remind myself that this is what they do. But in any case, either one of these will work. So I'm just going to quickly erase this one just to remove the amount of stuff on the screen. but this actually will attack here. So we're adding 2 carbons to this. And so I kind of draw this out, right? Again, I can put it here. I can also put it here. It doesn't matter. But I will be adding, looks like 2 carbons. I'll just add them here, right? Again, I could have put it up. I know I've been doing a lot of them like up here. That would have been fine. Just for drawing sake for the one, but I'll just put it down here just for sake of simplicity. You know, one really good tip. Now, this won't work 100% of the time, but one really good tip is that if you ever see an epoxide with 2 steps, okay, so an epoxide with 2 steps, where the second one is like some kind of H3O plus. H3O plus is acid, which means the first step must have been base. So that's another way to identify basic openings if you're not comfortable with them just quite yet. Again, this is not always the case because like here, we didn't really do it. Actually, you probably would have done it here. You probably would have seen it here. But this one, you don't really need it. But for these guys, you would. It's a nice little like hint, right? Again, not 100% of the time you're going to see it, but when you do see it, right, you know it's going to be basic because that's second step, okay? So if that makes sense, you can use it, or if it doesn't, it's okay. Just learn to recognize the first step as being base. What's another one? Let's do, I guess we'll just do another one of these. Okay, here's a new one. So lithium aluminum hydride. So there's 2 of these reagents, LiAlH4, which I will put here, and then we'll do this one here. NaBH4. You guys have probably seen these in your like list of reagents or whatever. These guys are H- nucleophiles. So actually what's attacking is H-, which is again a bit new for you guys. So H- would attack, again, less subside. H- would attack less subside. But what's really cool or interesting about these reductions is that essentially, you know, okay, let me draw it out. Maybe when I draw it out, it'll make more sense. When I open this up, right, H is what attacked. So you could draw the H out, but remember, we don't really draw H bonds. So it's almost like you're destroying the epoxide to reveal an alcohol. So it's like an interesting way of making alcohols, right? In real life, practically, right? If you were doing a reaction from an alkene, let's say, to here, and it wasn't really working out, like it just in real life it is working out, maybe what you do is you make the epoxide and then just reduce it. That's another way you could do this. Just some food for thought, right? To think about why this might be useful. But yeah, we don't have to draw the H out, so it can look like almost nothing happened. But something did happen, right? What we did was we opened the ring with the hydride, but we don't have to draw that H in. So in these cases, it's a bit hard to do the staple trace, right? Unless you draw it out, then it is, but yeah. So hydride's kind of interesting. Maybe again, something worth putting on your note card, something cool like that. Okay, cool. So just to summarize, right? If I'm in acidic condition, I'm going to get nucleophile attack on the more sub position. So attack here to open up as such, so nuke, more sub. I guess another way of saying this is that the alcohol is less sub. And if I'm in basic condition, right, I'm going to get the opposite. Right, so in this case, nuke less sub and OH more sub. So what's really nice, especially on the homework, maybe not so much on the quiz, but if on the homework, let's say that you're doing a problem like this one here, for example, and let's say the question is like H2SO4, CH3OH, right? And you recognize, okay, that's acid because H2SO4, so left versus right. I think I'm going to attack on the right side. Right. So let's say you say, okay, I think I'm going to attack on the right side. So what that means then is that this turns into OH, and then we'll add OCH3 here. Well, obviously, if you write this, hopefully you're like thinking, wait, what the heck did you just do? Right? This is wrong. Right? And the homework program will tell you that. They'll be like, oh, that's wrong. You have the wrong, opening. Well, guess what? If you drew the wrong relationship, right, or you drew the wrong type of opening, so this here would actually be the base opening. The way to fix it to make it acid is just switch to two things, right? Because that's what we see here, right? Nuke and OH basically switch places. So you can kind of switch these guys. Like that, and guess what? Now it's correct. Totally correct. That's great. So I guess this is more helpful for the homework, because on the quiz you won't know, right? But I guess if you're on the quiz and you had to figure out what the answer was, you kind of have a 50-50, right? It's either going to be this or it's going to be this. So you can 50-50, right? And all you have to do is switch the two groups. Okay, cool. And so, I guess essentially, I would really go through your notes. I don't know if there's, you guys are honestly so great to each other. I know you guys like send each other notes and stuff. I'm pretty sure someone has probably sent notes that has like the nucleophiles. I mean, I could check real quick right now, actually. I'm sure someone has. Let's see. Oh, wow. Someone sent notes. They're really nice. Really, really nice. Did I miss anything? I don't think so. Okay. Well, someone sent their notes and notes, which is, thank you. Let's see. Shout out to Vanilla Von Sweet. Vanilla Von Sweet. Looks like they started writing aromatic notes. No funny pictures in this one. Neither in this one either. Here, I'll give you guys a funny picture. That'd be a creepy picture, actually. This reminds me of that one TV show. I forgot the name of it. It was like the pyramid guy. He had that like kind of weird voice in the forest. Yeah, there's the funny picture of the day. Okay, anyways. But yeah, so I'm looking at their notes and it looks like there's a couple of nucleophiles. So go on there, familiarize yourself with them, or hey, note card time, right? So the best use of your note card is to do that. Cool. All right. So now that we have the reactivity down on how to open these, right? Let's talk stereochemistry. Stereochemistry is where this gets a little tricky because of the approach of the attack and everything. So, this is probably the part that you guys are going to watch the longest or probably rewatch a couple times, which is totally fine. Ask as many questions as you want. When it comes to epoxide stereochemistry, there are a couple different rules. So you might remember we talked about this. Let's say I have this guy here. And I epoxidate. Okay, so in this case, you can think about it. This would be MCPBA, right? And we get two isomers. So I want both isomers just so we can play around with them. Get a lot of stereochemistry practice. Cool. Whenever you do an epoxide opening, the first thing you want to assess or figure out is, does my epoxide have stereochemistry? Okay, so what I mean is, look at the epoxide. Okay, if it has stereochemistry, then you're going to have to manipulate the stereochemistry. Okay, if it doesn't, then you don't have to really care, and I'll show you an example of that towards the end. Okay, but let's say I have either of these epoxides, and I'll just do different reactions on them. So for example, let's do HBr. Okay, so we're opening up on that more supposition. Actually, let me just quickly check, were there any other acidic nucleophiles? No, not really. Yeah. Okay. So again, HBr, right? Again, we're going to get a protonation on this guy. And then who is Br going to attack? What side is Br going to attack? Br is going to attack left or right? Br will attack the left side. Okay. So because we're opening up on the left side, again, we can kind of get rid of that bond. but that bond that we didn't touch, that should stay the same. Okay, so we're attacking on this side here. Let me draw the arrow. So we'll attack on this side here. So we're breaking that bond, but we never touch this bond here. So that bond stays the same. Okay, that bond stays the same. When Br does its attack, though, because the bond is in the back, so it's a dash, Br is attacking from the wedge face, or in other words, right, we're doing an SN2 style backside attack, where we're going to see an inversion of the bond. Okay, so if I attack on this dash bond here, I'm going to invert that bond when bromine adds. Okay, so in other words, the nuke plus OH will always be opposite stereo / anti / trans, whichever term you want to use. Okay, so Br will always be opposite to the epoxide O. Okay, so if the epoxide O has to be dashed because it started dashed, Br must be wedged. They might be thinking, then what in the world happened to that methyl? Well, it got inverted, right? So now it's going to be a dash as well. Okay, so if your epoxide has stereochemistry, you will always invert the carbon that you attack. Okay, always, always, always. And then the side that you didn't attack just stays the same. So we could do the same thing here, SN2 backside. But let's, this time let's do NaCN. Okay, so NaCN, I mean, there is no H plus anywhere, so we know that this is a basic opening. Again, left or right, what side do we attack on? Just think about it. We attack on the left sub, so it's going to be right side. So we'll attack here. Again, we attack on the right side, so the left side stays exactly the same. On the right side, though, because CN attacked, it's a backside attack, and the CN must always be opposite to the OH. Right? We are going to get an inversion. CN is going to attack like that. Okay, so OH and CN will always be opposite. All right, really with this kind of thing, you just need to do a bunch of practice. So that's exactly what we're going to do. Just get a bunch of practice in so we can, really understand this. So I will do, let's do this here. Okay, let's do lithium aluminum hydride and an H3O plus. Again, second step acid means the first step must have been base. So when this H minus here attacks, right, left or right side, this is basic. It's going to be right side. Okay, so we'll attack here. Again, this side should stay the same. We did not attack it. But when H minus attacks, what's it going to be? Right? It's always got to be opposite. Okay, so I mean, you could put an H here. I'll be honest, this should kind of make you feel like it's wrong because it is. So the H is actually going to be down here. Which I guess now I kind of feel a little dumb because I guess back here I just kind of didn't care about that, did I? Okay, I apologize. I should have been a bit more careful with that. Did I make that mistake anywhere? I don't know. I'm trying to see if I drew any like really odd. Oh yeah, this one. Oof. Yikes. Cringe. What was I thinking? Don't know. Anyways, it's late. Oh, actually, I kind of fixed it here. Okay, whatever. Anyways. So it'll be down there. But it's okay because remember, when it comes to H, we don't even draw it in. But you can. One thing she could do is she can change H into D. So that's deuterium. Don't be thrown off by that. It's just heavier hydrogen. It's hydrogen, just heavier. D you would have to draw in because it's not hydrogen. So that's one way she can modify it so that you have to, draw it in. Cool. Let's say that I did H2SO4 and methanol. Right, again, where is it going to attack? It's going to attack here. And again, because my epoxide has stereochemistry, right? So when I draw this in, again, it's going to look like that, but that should kind of throw you off and tell you that it's wrong. If not, it's okay. It's okay if you don't. I mean, if you draw like this, it's fine. You can still prove that it's correct, right? But it should go down here. And then again, if we attacked here, that means that the methanol will be OCH3 as a dash. And then remember that methyl that was a dash just comes to the front as a wedge. And you can draw it this way. That's fine. Or you can draw it this way. That's totally fine. It's up to you. I'm just going to draw it this way because to me, that looks nicer. But if it looks nicer to you on the other side, by all means, you can do that too. Okay. So again, that incoming nucleophile and the oxygen from the epoxide, they've got to be anti to each other. They've got to be opposite if the epoxide has stereochemistry. Okay. Now, if you're really lucky, get an epoxide like this one. So why am I lucky if I get an epoxide like this one? Well, let's say that I do a basic opening. So basic opening attacks here. So that means that this bond stays the same. And then maybe I draw this. Well, if you stare at this, maybe you'll see it. It's okay if you don't. Actually, yeah, let's write something else. So OH3 minus OCH3H, right? Like that. So basic condition. You could draw this. This is totally fine. Or you can draw this going down. That's totally fine. But this carbon is not chiral. Not chiral. So who cares where it is in space? It could be anywhere. So again, all this stereochemistry stuff really only matters for chiral carbons. You could draw it in. You won't get penalized, but you can also just get away with not doing it. So that's always usually a nice one. Now you could also do an attack on the Morse sub, obviously. So we did like the HI attack, I guess. So attacks here. Same kind of idea, right? I is always going to attack such that it is such that it comes opposite to that dash bond. But OCH3, I mean, you could show it as a dash if you wanted to. That's totally fine. You could show that. Or because it's not chiral, just don't show it at all. Okay, so pretty nifty little trick there. Okay, so again, if your center is chiral, or sorry, if your epoxide has chirality or has, wedge and dash, be sure to apply the inversion, right? That will put you on the right path. Now, what happens then if my epoxide is not chiral, or sorry, it does not have dash wedge, but my local substituents do? Well, guess what? You are very much in luck, because the only time inversion matters is when the epoxide has stereochemistry. If it doesn't, if it's planar and you do an opening, like let's say, let's do like a NaN3. No, let's not do that. I want to confuse you guys. Let's just use this one again. So alkyne. So this is, again, basic opening. So left versus right. It's going to open on the left. So it'll attack here. Okay. When the epoxide has no stereochemistry, all you have to do is make sure that, okay, let's say that it opened up this way. Look like this. Just make sure that the nucleophile is on the other carbon facing the opposite way. So it kind of makes this like zigzag kind of thing here. Okay, so it makes that kind of zigzag. Keep the stereochemistry of the groups the same. So ethyl was a wedge, methyl wedge, ethyl is a dash here. And there you go. That's your answer. So stereochemistry should only be inverting if the epoxide has stereochemistry. If it's planar, keep everything the same. Just make sure to follow the zigzag. So let's say that I did this in acidic. So H2SO4 and ethanol. Again, that's going to attack here. So again, if I kind of draw the opening, this will be here, right? I want then the ethanol here. And I keep everything else the same. So this is a wedge. Methyl wedge, ethyl dash, and then methyl wedge. Keep that exactly the same. Okay. Let's say that I have, I mean, you'll notice that these all just kind of like come back to be the same thing. So pH is just something random, don't worry. Let's say that I have that, and I do, I don't know, this is, yeah, let's do this, MGBR. So that was that one that's like, it's like basic condition, right? Where you attack with the carbon, right? We can attack on the left side or on the right side. It's basic, so we attack on the right side. So again, you can kind of just draw this in. You want this to be here. And then this stays the same. And this also stays exactly the same. Exactly the same. Okay. To kind of help you guys, this one might be a hard one to visualize. Essentially, what you're doing is you're replacing the MGBR with the bond onto the epoxide. That's how these, we call these Grignards or organometallics. So these organometallics tend to react. Let me try to do a simpler one too. Hopefully that'll help you guys out. So let's say we have this one here. Let's say we have like a propyl Grignard, right? Again, that's going to attack on this side. The OH here, right, from the epoxy. And then 1, 2, 3, 3 carbons, right? You're going to add that to this carbon. 1, 2, 3. There you go. And then just add that in like that. Okay. If there was like something else here like that, you just add it in. Okay. Cool. So those are the stereochemical tricks for epoxide openings. I imagine it's not going to be too crazy. I mean, you can do it practice and you'll see how bad it will get. But the general rule of thumb, right? If your epoxide has stereochemistry, right? If it has stereochemistry, then you will be doing inversions, right? You will be messing around with the stereochemistry. You will have to know if the epoxide's a dash, right? You'll have to know, okay, it's going to react on the wedge face, right? The nucleophile. So it'll be opposite to each other. So you see that they're opposite, they're anti, they're trans. You see that in their bond stereochemistry. One's wedge, one's dash, one's wedge, one's dash. When there is no stereochemistry though, right? Don't worry about it. Just make sure to draw them in that zigzag. Here's the thing. When they're in a zigzag like this, that's anti-trans. So you're still obeying the rules. We're not breaking any rules or, it's not like the rules didn't work. It's just, this is just a different way to represent trans, or a different way to represent anti or opposite. Okay. It's just how it works with these systems. Okay. Cool. Well, with that being said, that is ethers, right? And epoxides. Again, I know I probably rushed through this a little bit, especially through the end there, because, it's hitting that 2-hour mark and it's getting late. And, it's a lot of material. So always, 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 this is just like a supplementary viewing. Ask a lot of questions, do your homework, right? Ask questions, do the practice problems, ask questions. I mean, actually, I guess I can talk about this, but as some of you guys might know, I recently was given a job offer by a really big, nice company. And I am probably going to take it just because I want to work in this field and I like money. Sorry to say. But all that really means in terms of, my ability to, obviously if I have a job, I won't be as available to answer questions, but, I'll always make time for the 8 class. You guys are really fun to talk to, and it's always really easy to tutor this class. So by no means, don't worry about me disappearing or anything. I'll definitely still help you guys out, especially, if it has to go down to it, it'll just be on the weekends, right? But that's okay, because the weekends are always when I make these videos and they're right before the quizzes. So it's like perfect kind of timing. So by all means, always ask questions, right? I'll try to get to them. But yeah, if there's anything confusing, let me know. If there's anything that I might have made a mistake or I might have missed,